Hi, this is our multimeter code using an OLED screen and a Rotary encoder. There's a little disclaimer for this code. It doesn't work the way we intended it to. We had a lot of last minute changes and we weren't able to tinker with it as much as we would have liked to get it to work properly. What's wrong with the code is that the timers used to get the inductance and the timers for the encoder kind of clash together, so it doesn't allow the code to work properly or the circuit to run the way it's supposed to. So we hope that future classes, if they use this code, are able to fix the issue or add on to it to make it better. But here we go. This first line is used to find the address for the OLED so we can start communication with it. These two are the libraries for the OLED for the screen, and then to draw shapes and text. Right here we define the display screen for the OLED. It's 128 pixels wide and 64 pixels tall. This is the address of the OLED display. And then we use this display to represent the OLED screen in the code. And here are the encoder pins. Pin 2 is used for the first signal pin. Pin 3 is used for the second signal pin. And pin 4 is used to press the button on the encoder. Here we have the encoder variables. This is used to store the encoder's current position, and it's volatile because it could change unexpectedly due to the interactions with the user. And then just right here it tracks the last position of the encoder to determine if it has moved. And this right here is used to tell us which menu item will be highlighted. And this is used to determine if the button is pressed or not pressed. And then this names the menu option we'll be having, which is the ohm, capacitor, inductance meter. And then the default is menu, so no meter mode is selected at the start. And here are the ohm meter variables. Read is used to get the voltage reading for our unknown resistor at analog pin 83. R1 is our unknown resistor, and R2 represents our known resistor values. And then these pins are used for our known resistor values. This is pin 8, 7, 6, and 5. And their corresponding values, which is 1K, 10K, 100K, and 1 megohm. And these are the values. And this keeps track of what R2 is selected. This is our capacitor meter variables. Analog pin 82 is used to measure the voltage of the capacitor. Charge pin 11 is where our charge resistor is connected. Charge pin 10, discharge pin 10 is where our discharge resistor is connected, which is a 220 ohm resistor. Tau is used to measure how long the capacitor value takes to charge, so we could later calculate the capacitor value. And then R, which is our charge resistor, is a 2 meg ohm. This large resistor value is used so we can measure large and small capacitor values. And C used to C is just for the capacitor, and this is for the units. And this is for the inductor meter variables. Have poles to measure the wavelength with the capacitance value of 2 microfarads. And then FP2 stands for pi squared, which is used for the formula to calculate the inductance value. In setup, we begin the serial monitor just to make sure things are running correctly. And we set up the OLED display, clear the screen, and set up the encoder pins. This is used to detect when the encoder is changed. And this is just used to set up the R2 values for now. We display the menu in the OLED. And here in the loop, we check if the encoder button was pressed, and we allow a small delay so it prevents multiple presses. If the button was pressed, then we go to a selected meter mode. If not, we just reset the encoder position every time. When the encoder button is released, we show the menu. This is used to display the menu on the OLED screen. And then once 1 meter is selected, it takes you to its corresponding meter code. Right here in the void display menu, we display the meter options in the OLED screen. And here in the void encoder, we just store the encoder values and turn it into something that Arduino can read. Right here, this determines if the encoder is turned clockwise or counterclockwise. And then we save the current position. Right here, it takes you to the resistor meter code. This displays a little index. Once the resistor meter is selected, it gives you 4 R2 values you could choose from, which is the 1K, 100K, 10K, 100K, and 1 megohm. It's displayed on the OLED screen. And then right here, just so the encoder keeps track of which R2 value is being chosen. Once an R2 value is selected, it displays the value you have selected and proceeds to do the calculations. Right here. And this is the calculations used to determine R1. We display the unknown resistance, which is R1, and the known resistance that the user chose, which is R2. If R1 value is less than R2, it asks the user to increase the scale. If not, it displays the resistance value for R1. And another little disclaimer for the resistor code. It does not display the proper resistor values. So if future classes or just coder enthusiasts want to go through the code to determine why that's the cause, feel free to do so. And this is our capacitor meter code. The OLED screen is updated to display the capacitor meter. We start charging. This is used to set the charge resistor to output so the capacitor is not charged initially. We set it to high, the resistor to high, so the capacitor starts charging. And right here, we start taking the time. Right here, this line represents the voltage the capacitor reaches to display a valid capacitor value. Arduino reads voltage as bits, so 5 volts would be 1023, and this would be 646 would be around 3.6 approximately. We found that this number is best to calculate the capacitor value. It gives us a closer capacitor, a closer true capacitor value than using 647 or 648. Whichever works better for you. But in this line, at analog to 8 waits until the capacitor voltage reaches this. Like I said, it's about 3.16 to get us a closer capacitor value. And then this is the tau. We use tau to then calculate capacitor value by using the time it takes to charge and dividing it by the resistor value. And then if the unit is in microfarads, we print microfarads. If the capacitor value is less than 1 microfarad, we convert it into nanofarads. And right here, we display the capacitor value on the screen and give it 2 decimal points. We then set the charge pin to low so it stops charging the capacitor. And then once it reaches 0, we then start to charge the capacitor again. But wait 2 seconds before doing that. And this is for our inductor meter code. Right here, we update the OLED screen to show that the inductor meter was selected for 2 seconds. And then we use pin 12 to read the oscillation signal of the comparator. And then pin 13 sends a pulse, a trigger pulse, which is through the resistor, so it starts charging the inductor. And then the pulse is turned on to give us a high pulse, which is the top of the sine wave. And then it turns to low to give us the bottom of the sine wave. And then right here we have pulse equals 10 because this is what was the original line, but this is where the timer kicks in. And if we add this line, like the way it was supposed to, it doesn't update our OLED screen because the timers start to interfere too much. So it stops making, so it makes the code stop functioning correctly. Right here just is to give us a pulse value or an inductor value, just to make sure it's working otherwise. And then right here, if a pulse is detected, we use the period, which is 1 full cycle, to then calculate the inductor meter. And like I said, for our previous inductor meter, we used this number to make up for the IR loss, so this might not be necessary for this code, but we don't know for sure. And then we display the inductance value. If there's no valid signal, we display no signal. Thank you.